In this video, we will learn how to compute the sample size for proportions when our goal is to construct a confidence interval on the difference or the risk ratio or the odds ratio of the proportions in two samples. Okay, so let's see. So let's say that we are studying a pulmonary disease, this chronic obstructive pulmonary disease, and we wonder whether there is a difference of people. So we have smokers performing a sport, and then some of these smokers will develop this disease. Some of these smokers performing a sport will also develop this disease, and then we wonder if there is a difference in the proportion of diseased people between the group of smokers or between the group of smokers making a sport. And we want to construct, so let's say that the first group will have a proportion P1, the second one a proportion P2. We want to compute the difference between the two, and we want to give a confidence interval for this difference. And we want this confidence interval, the half width, to be delta that is 3%. So the error, so the confidence interval to the left will be -3%, to the right +3%. And we expect the two proportions to be around 13%, and we will have the same number of individuals on both groups. So how do we calculate the sample size? So first we need to define the difference. So we will compute the proportion in the first group, we will compute the proportion in the second group, and then we will compute the difference between the two. If the Gaussian approximation is valid, then this proportion will be the variance of this delta will be the variance of the first one plus the variance of the second one. And if the Gaussian proportion is valid, the Gaussian proportion is valid when P1 times N1 is larger than 5 and 1 minus P1 times N1 is larger than 5. And the same for the second group. So this will be the variance of this will be the variance of this. And we want to construct a confidence interval of this form, so we will observe some difference, and then the confidence interval has to be of the form this value minus delta, this value plus delta, and this delta for the Gaussian, it is this one. So now we have everything to compute the sample size, and we may even allow for different numbers of individuals in both groups. So let's say that one of the groups is much more difficult to obtain than the other one, then we can define this ratio between the size of N1 and N2, and we have everything to solve our equation. So we solve it, and N1 has to be larger than this and N2 larger than that. And we see that it follows the general Gaussian sample size calculation. So it has a term that depends on the confidence interval, on the level of confidence, and then divided by the normalized effect size. So the normalized effect size, here it is delta divided in this way, and here it is delta divided in this way. You may look at the R. So the R here, let's say that you want more people in group 1. So if you want more people in group 1, R will be larger than 1, and then this somehow this R larger than 1 makes N1 to be larger than N2. So for instance, in our case, we wanted both groups to be of the same size. So R is equal 1, P1 and P2 are more or less approximately around 13%. So we have that N should be larger than this, that is 9066. So we need a lot of people because we wanted the delta to be very small. So we wanted to construct a very precise confidence interval. Okay, so what if we want to construct a confidence interval for the risk ratio? So the risk ratio is the ratio between the P1 and P2. So we have the same problem as above, but we want to construct a ratio uh, the risk ratio confidence interval with a precision of 20%. So this delta that we had before is 20%, and we expect the proportions of smokers and non-smokers developing COPD. It was non-smokers, right? It was smokers and smokers doing sport. We expect them to be between 15% and 11%. Okay, so the risk ratio is not normally distributed, but the logarithm is normally distributed. And this is the variance of this logarithm of the risk ratio. So now we will construct a confidence interval that is of log this minus delta, log this plus delta. And we want this delta to be because it follows a Gaussian, this delta has to be this one. And again, we can construct a confidence interval. We know everything now, so we can solve for n, and we can also allow for different group sizes if one of the groups is more difficult to obtain than the other one. And the kind of formula that we have is similar to what we had before. And yeah, so this R was equal to this because we defined it in this way. But now that we know what N1 and N2 are, we can substitute. We can see that it takes this value, and this value is 1 over the square root of the odds ratio. See, so this ratio here is called the odds ratio. Okay, so yeah, so let's say that the risk ratio we expect it to be around 136, so meaning that it is 36 times more likely to develop COPD in one of the groups than in the other, and then we will because the two proportions are slightly different. The optimal allocation is given by this one. So this risk ratio is giving us the optimal, the minimum size of N1 and N2. So R should be this one, so that the group that is more variable, it is sampled more, and then you simply substitute in. We have N1 is equal to this, that is 1500, and N2 is 1200. Okay, so what happens if we do it with odds ratios? So if we do it with odds ratios, now the odds ratio, we also want to have a confidence interval with a 20% of precision. So the odds ratio is defined in this way, and again, if n is large, the odds ratio, the logarithm of the odds ratio is normally distributed. So this is the variance of the logarithm of the odds ratio, and we follow the standard procedure. So the optimal sample size, that is this one, is given by this 1 over the square root of the odds ratio that we expect, and then we simply follow the Gaussian sample size calculations formulas. In this case, the odds ratio is around 0.7. So this you may recognize this is P1, 1 minus P1, P2, 1 minus P2, and this odds ratio doesn't mean that smokers doing sport have 30% less chances of developing the disease. So and the optimal allocation is again the same one, And if you want to have such a high precision in the odds ratio, so 20% of precision is pretty high, you need many individuals, 2600s, 2200s. This would be all for the construction of confidence intervals of two samples.